Why does an industry defined by cutting-edge aerodynamics, ultra-lightweight composite materials, and multi-million-dollar branding campaigns choose to cover almost every single one of its flagships in the exact same color? If you stand at the window of any international airport terminal, you will see a monotonous sea of white fuselages. It looks like a failure of imagination. But in the world of commercial aviation, where every gram of weight is calculated and every minute of maintenance is billed, design decisions are never cosmetic. The choice to paint a passenger jet white is not a matter of style. It is a matter of survival, physics, and economics. To understand the scale of this design convention, consider the sheer volume of paint required to cover a modern commercial airliner. A narrow-body aircraft, such as the Boeing 737-900, requires approximately 190 liters of paint to cover its exterior surfaces. This liquid layer, once dried, adds roughly 90 to 110 kilograms of weight to the airframe. For a twin-aisle wide-body aircraft like the Airbus A350-900, the surface area expands significantly. It requires upwards of 360 liters of paint, adding more than 250 kilograms of dead weight. Over the course of a single year of flight, carrying that extra weight consumes thousands of liters of jet fuel. Yet airlines willingly pay for this weight penalty, and they apply it almost exclusively in white. In fact, more than 70% of the commercial aircraft operating today wear a primary livery of plain white. This raises a fundamental question. Why does a global industry, which spends billions of dollars annually to shave fractions of a percent off its fuel consumption, choose to carry hundreds of kilograms of paint? And why has it settled almost universally on the same monochrome finish? The answer to this question begins in the middle of the 20th century, an era when commercial aviation looked fundamentally different. If you walked onto a tarmac in the 1960s or 1970s, you would not have seen a sea of white paint. Instead, you would have seen bare, polished metal. Airlines like American Airlines, Eastern Airlines, and Northwest Orient flew fleets of passenger jets that gleamed in the sunlight, showing off their raw aluminum skins. This design choice seemed entirely logical at the time. By leaving the fuselage unpainted, airlines completely avoided the weight penalty of paint. An unpainted aircraft was a lighter aircraft. A lighter aircraft burned less fuel, which lowered operating costs and allowed for slightly longer flight ranges. For decades, the polished silver look was synonymous with the modern jet age. It conveyed speed, strength, and technological progress, reflecting the bare metal construction of the aircraft themselves. But aluminum is not impervious to the environment. When exposed to the elements, bare aluminum reacts with oxygen and atmospheric moisture, leading to oxidation. On a coastal tarmac, salt spray from the ocean accelerates this process, causing pitting and surface corrosion that can compromise the structural integrity of the fuselage. To prevent this decay, unpainted aircraft required continuous, intensive maintenance. Teams of workers had to polish the metal surfaces regularly using mechanical buffers and specialized chemical compounds. A single wide-body aircraft required thousands of hours of manual labor every year just to keep the aluminum bright and protected. Furthermore, the polished surface did not protect the metal from the tiny abrasions caused by dust, ice crystals, and rain at high speeds. Eventually, airlines realized that the labor costs and the maintenance downtime associated with polished aluminum were offsetting the fuel savings of a lighter airframe. The industry needed a solution that would protect the metal without requiring constant manual labor. The breakthrough came when engineers shifted their perspective from weight reduction to thermal control. An aircraft is a complex thermodynamic system. When it is parked on the ground, particularly in hot climates, it is exposed to intense solar radiation. The metal skin of the fuselage behaves like a massive radiator, absorbing thermal energy from the sun. On a hot summer day with ambient temperatures of 40 degrees Celsius, the skin temperature of a dark-painted aircraft can easily climb to over 80 degrees Celsius. This heat conducts inward, warming the cabin interior to uncomfortable levels and putting an immense strain on the aircraft's onboard cooling systems. To combat this, engineers turn to the physics of light reflection, specifically the albedo effect. Albedo is the measure of how much solar radiation a surface reflects rather than absorbs. By coating the fuselage in white paint, engineers found they could reflect up to 80% of incoming solar radiation. This simple change had profound consequences for aircraft operations. When an aircraft is parked at a gate, it must maintain a comfortable cabin temperature for passengers boarding the flight. If the skin of the aircraft is hot, the environmental control systems, commonly known as the air conditioning packs, must work significantly harder to cool the cabin air. These packs run on compressed air bled from the aircraft's auxiliary power unit, a small gas turbine engine located in the tail. Running the auxiliary power unit consumes jet fuel. By painting the fuselage white, airlines kept the cabin skin temperature close to the ambient air temperature, drastically reducing the energy required to cool the interior. This saved thousands of kilograms of fuel before the aircraft even pushed back from the gate. Keeping the structure cool reduced the thermal stress on these systems, extending their operational lifespan and improving reliability. But this thermal protection became even more critical with the arrival of modern composite materials. In the 21st century, aircraft design underwent a material revolution. Classic aluminum alloys were largely replaced by carbon fiber reinforced polymers, which now make up more than 50% of the structural weight of advanced airliners like the Boeing 787 and the Airbus A350. Carbon fiber is incredibly strong and light, allowing for higher cabin pressure and larger windows, which improves the passenger experience. However, these composite materials have a distinct physical vulnerability. They do not tolerate heat in the same way aluminum does. Carbon fiber composites consist of thin carbon threads embedded in an epoxy resin matrix. If this resin is heated beyond its glass transition temperature, the point at which the polymer shifts from a hard, glassy state to a soft, rubbery state, the material loses its stiffness and strength. For many aviation-grade composites, this transition begins at temperatures around 80 to 90 degrees Celsius. To prevent this structural compromise, composite aircraft must be painted white. The white polyurethane topcoat acts as a thermal shield, ensuring that the composite skin temperature never approaches the critical limits of the resin. Without this thermal barrier, the use of lightweight composites in modern commercial aviation would be virtually impossible. If you want to understand not just what flies over your head but why it's built that way, subscribe to Flight Simplified and stay with me. Beyond thermal management, the choice of white paint serves a second, equally critical purpose. It acts as a visual safety diagnostic tool. Every time a commercial aircraft completes a flight, it must undergo a rigorous pre-flight inspection. A flight crew member or a maintenance technician walks around the aircraft, examining the fuselage, wings, and engines for any signs of damage. They are looking for hairline fractures in the metal skin, loose rivets, bubbling paint that suggests corrosion beneath the surface, or dents from bird strikes and runway debris. They are also searching for fluid leaks. Modern aircraft rely on complex hydraulic systems operating at pressures of up to 3,000 pounds per square inch to move control surfaces like flaps, rudders, and landing gear. If a hydraulic line develops a microscopic leak, the fluid, which is often colored amber or purple, will escape and spray along the fuselage. A clean, bright white background provides the maximum possible visual contrast. Under the beam of a flashlight during a nighttime inspection in the rain, a dark streak of hydraulic fluid or a thin black crack in the fuselage skin stands out immediately. On a dark blue, red or black fuselage. These critical safety indicators are easily lost in the shadows, potentially allowing a minor defect to develop into a catastrophic structural failure. This visibility is also vital when dealing with the harsh radiation environment of high-altitude flight. At cruising altitudes of 11,000 meters, an aircraft flies above the thickest layers of the Earth's atmosphere. Here, the protective shield of air is thin, exposing the aircraft to intense solar ultraviolet radiation. These rays break the chemical bonds of paint pigments, a process known as photodegradation. Colored pigments, particularly organic reds and blues, absorb ultraviolet wavelengths and break down rapidly, causing the paint to fade, oxidize, and lose its gloss. White paint is formulated using titanium dioxide, an inorganic pigment that is exceptionally stable and highly efficient at scattering ultraviolet light. Because it reflects this energy rather than absorbing it, white paint prevents the chemical breakdown of the polyurethane binder. As a result, it retains its physical integrity and appearance for much longer than colored coatings. Reducing repainting frequency is a major financial priority. Repainting a commercial aircraft is a labor-intensive process that takes the vehicle out of service for up to 2 weeks. The aircraft must be flown to a specialized hangar where the old paint is chemically stripped or blasted away. Technicians sand the entire fuselage before applying multiple layers of primer, base coat, and polyurethane top coat using electrostatic spray guns. The entire operation can cost between $100,000 and $200,000. More importantly, every day the aircraft spends in the hangar is a day it is not generating revenue. By using white paint, which lasts longer under intense solar radiation, airlines can extend the intervals between repaints, maximizing the operational availability of their fleet. This financial efficiency extends to the business model of modern commercial aviation. The majority of aircraft flying today are not owned by the airlines operating them. Instead, they are owned by leasing corporations that lease them to various carriers worldwide. When a lease expires and the aircraft is returned, it must be quickly prepared for the next operator. If the fuselage is painted in a highly customized, colorful livery, the lessor faces a massive expense to strip and repaint the aircraft. To avoid this, the industry has adopted the Eurowhite design standard. Under this approach, the main body of the fuselage remains a simple, uniform white, while the airline's branding is restricted to the tail fin and a few vinyl decals. When the aircraft changes hands, technicians simply peel off the old decals and apply new ones, leaving the base paint intact. This allows the aircraft to be put back into service in a matter of days rather than weeks, reducing the friction of aircraft transactions. While financial and operational factors dominate the decision, safety engineers have discovered an unexpected ecological benefit: the prevention of bird strikes. A bird strike, a collision between an aircraft and a bird, is a significant hazard, capable of damaging nose cones or causing engine failures. Research suggests that fuselage color plays a role in how effectively birds avoid oncoming aircraft. Avian vision is highly sensitive to contrast. When a dark-colored aircraft flies against a dark ground or a cloudy sky, it has low visual contrast, making it difficult for a bird to detect. A white fuselage, however, provides a stark contrast against the blue sky, clouds, or the earth. This high contrast allows birds to spot the approaching aircraft from a greater distance, giving them valuable fractions of a second to react and dive out of the flight path. When you combine all of these elements, the white paint covering a modern passenger jet ceases to be a simple choice of color and becomes a highly engineered safety system. It is a thermal barrier that keeps composite structures from weakening under the desert sun. It is a clean canvas that exposes critical structural cracks and corrosive fluid leaks before they can threaten a flight. It is a protective shield against the destructive forces of solar radiation, an economic framework that facilitates the leasing of thousands of aircraft, and a visual warning sign that helps wildlife avoid collision. Every element of the aircraft is designed to perform multiple functions at once, and the paint is no exception. The next time you look out an airport window at a line of passenger jets parked on the tarmac, you will not see a lack of creativity. You will see a refined engineering choice. You will see a protective layer of white polyurethane catching the afternoon sun, maintaining a stable temperature for the passengers boarding inside, and shielding the carbon fiber frame from the elements. It is a silent partner in the complex machinery of flight, working constantly to ensure safety, efficiency, and reliability with every departure. Until next time, this is Flight Simplified.